Within our lifetimes, we might get a ping that changes history. Not a blurry UFO clip, but an unmistakably artificial pattern from another star. A narrow tone that drifts with a planet's rotation. A laser flash counting in prime numbers. A planetary spectrum with the fingerprints of industry. How likely is that? What are we actually listening for? And if intelligent life is common, where is everybody? We'll walk the numbers, the Drake equation, visit the wow signal, unpack technosignatures we can detect today, and face the Fermi Paradox with what modern astronomy really knows. 30 years ago, the number of confirmed planets beyond our Sun was 0. Today, it's thousands, with many more candidates. Kepler taught us planets are everywhere. Hot Jupiters close to their stars, super-Earths we don't have here, mini-Neptunes, and a decent fraction orbiting in temperate zones where liquid water could exist, at least on paper. TESS now scans almost the whole sky, catching worlds around bright, nearby stars we can follow up. JWST is already tasting the atmospheres of a few, water vapor here, carbon dioxide there. Exoplanets flipped the question from, are there planets, to how many could host life, and how many might host technology we can detect from light years away. Detectability is the key word, because physics and budgets decide what we can actually find. In 1961, astronomer Frank Drake proposed a way to structure this giant unknown. It multiplies 7 terms to estimate how many communicating civilizations might be detectable in our galaxy right now. First, our star, the rate of star formation in the Milky Way. A few new stars per year is a fair estimate. FP, the fraction of those stars that have planets. That looks high. Most stars seem to have planetary systems. NE, the average number of potentially habitable worlds per system. Maybe one or more, depending on your habitable zone, definition, and atmosphere assumptions. FL, the fraction of those worlds where life actually arises. Here we have one data point, Earth. Did life appear quickly, once conditions allowed, or did we get lucky? FI, the fraction where life becomes intelligent. Earth took billions of years to go from microbes to minds. Is that typical or rare? FC, the fraction that developed detectable technology, stuff that leaks or purposefully beams signals. And L, the average lifetime of detectability. Do they stay on the air for centuries, millennia, longer? If your guesses are optimistic, you get thousands of coexisting civilizations. If you're pessimistic, you get us, alone. The equation doesn't give a single answer. It's a flashlight that shows where our ignorance lives and which measurements help most. Let's zoom into habitable. The classic idea is simple: a zone where liquid water could exist on a rocky surface. But real planets are messy. Many of the most common stars are M-dwarfs, small, dim, long-lived. Their habitable zone is close in, where planets can become tidally locked, one face permanent day, the other night. That's not necessarily a deal-breaker if they have thick atmospheres to move heat around, but flares from young red dwarfs can blast them with radiation and strip those atmospheres. Multi-planet systems like TRAPPIST-1 are tantalizing. 7 Earth-sized worlds, 3 in the temperate zone. But density, composition, magnetic fields, and water inventories matter. Ocean worlds could exist, with deep global seas capped by high-pressure ice. Life there might thrive in the depths, detectable only if it changes the atmosphere. Some planets might be desert worlds with thin air. Others could be mini-Neptunes with puffy gas envelopes. Habitable on paper doesn't always mean habitable in practice, and habitability doesn't promise intelligence. So what does detectable technology look like from light years away? Radio is the classic. A narrow band tone, a purely artificial-sounding whistle, stands out against natural noise. There's even a favored part of the dial, around the 1.4 GHz hydrogen line between hydrogen and hydroxyl, nicknamed the water hole. A beacon there would be poetic and practical. We also look for carriers that drift in frequency with a planet's rotation and orbit. That Doppler wobble is a signature you can't fake easily. Optical SETI hunts nanosecond laser pulses, brief flashes that can outshine a star for an instant. Waste heat is another idea. If a civilization surrounds its star with a swarm of energy collectors, the starlight they use comes back out as heat, glowing in infrared more than expected for that star. And then there's atmospheric technosignatures. Gases like chlorofluorocarbons, industrial chemicals, are unlikely to be produced in bulk by biology. With future telescopes, we might spot them in a transiting planet's spectrum. Projects like Breakthrough Listen feed giant dishes millions of targets and petabytes of data. Algorithms trained to spot narrow lines, drifting tones, and repeating patterns sift through it. The closest brush we've had with a truly weird signal came in 1977 at the Big Ear Radio Telescope in Ohio. A sharp, 72-second narrowband spike appeared near the hydrogen line. On the old-school printout, an astronomer circled it and wrote one word: "Wow." It looked exactly like the kind of thing you'd hope to see, but it never repeated. Follow-up scans found nothing. Later ideas suggested a natural source, like neutral hydrogen from a passing comet, though that's still debated. In SETI, a single unrepeatable event stays a mystery, not a detection. The bar is repeatable, verifiable, and ideally seen by independent instruments. Now the uncomfortable question, framed by physicist Enrico Fermi. If civilizations arise often and can travel, or at least send self-replicating probes, the Milky Way could be explored in tens of millions of years, an eye blink of galactic time. Yet we don't see obvious galaxy-spanning engineering, and we haven't verified any signals. Why? Explanations range from sobering to hopeful. Maybe we're early. The first wave of civilizations around sun-like stars is only now emerging. Maybe the galaxy is hazardous. Supernovae, gamma-ray bursts, and mass extinctions reset planets. Intelligence might be rare. Technological lifetimes might be short if species self-destruct or go quiet. There are also sociological ideas. Maybe advanced beings use communication methods we're not listening for, or they choose to be quiet. The zoo hypothesis suggests they deliberately avoid disturbing developing civilizations. The dark forest idea imagines everyone hiding for safety. And then there's a humbling practical point. The part of signal space we've searched is tiny. We've listened to a sliver of frequencies for short windows toward a small fraction of stars. We've sampled a glass of ocean and concluded there are no whales. Real first contact is likely to be a pattern, not a picture. A narrow tone turning on and off with a planet's day-night cycle. A laser cadence that ticks through prime numbers. A transit spectrum with industrial gases that biology can't make in bulk. Multiple clues will help, because each alone can have natural imposters. Even city lights are testable in principle. If the night side of a planet is brighter than expected at certain wavelengths, that could hint at artificial lighting. It would be faint and controversial, but it's something we can look for with future telescopes. And if we do see a candidate signal, the protocol is verification. Point other telescopes, rule out satellites, aircraft and reflections, check for repetition, share data. Great science is cautious and public. The search is scaling up. The square-kilometer array will be the most sensitive radio array on Earth. Upgrades to Breakthrough. Listen broaden the number of stars and the bandwidth we can scan. The extremely large telescope and the Giant Magellan Telescope will help read exoplanet atmospheres. NASA's proposed Habitable Worlds Observatory is designed with biosignatures and technosignatures in mind. Each year, our search volume grows. Silence today isn't no. It's not yet. If intelligence is out there and broadcasting or leaving tech fingerprints, we're getting better at noticing. And if one day a narrow line appears again, repeating with a rhythm only intelligence would choose, you'll hear it here, with sources you can check. If you want a science-first alert, when a credible candidate drops, subscribe and ring the bell. What technosignature do you think we'll spot first? Tell me below.